if you remember, during the past 3 weeks of our lecture sessions, we referred to different kinds of inventory problems, and these inventory problems are appropriately classified. In the last week, that means during the third week of our lecture sessions, we referred to static inventory problems under risk. During this week, that means during this fourth week of our lecture sessions, we'll be exclusively dealing with the static inventory problems under uncertainty. Okay, so and during this week, all these 5 lecture sessions will highlight the different aspects of static inventory problems under uncertainty. Now this sort of problem in inventory management you frequently come across, and so obviously when you come across such a problem, first thing you need to do, that is you need to formulate the problem, and then once the formulation is over, you suggest the appropriate solution techniques. So this is the general the rule we will follow. Now lecture 1, we will be discussing general characteristics of the problems you should be aware of, the possible decision criteria under uncertain condition, the two specific the decision criteria we will discuss. The first one is World criterion and the second one is the Savage criterion. During lecture 2, we will be referring to Bayes criterion, and then we will discuss the problem formulation with partial information. During lecture 3, the well-known Chebyshev and other inequalities as you find in the probability theory we will be referring to, we will discuss with numerical examples. In the next lecture session, we will be again continuing with the numerical examples. You should be aware of the different kinds of formulations, and against each formulation, against all these formulations, you also should be aware of the numerical problems. So we will be continuing our discussion on numerical examples, and then a specific the formulation we will discuss in detail, that is the determination of the order quantity when the understock cost is estimated per unit basis. So this is just one class of problem, and we will be specifically dealing with this problem. During the last session of this particular topic, what are the important points you should remember? So we should summarize all these important points, and we will refer to the dynamic inventory problems under uncertainty. This is just an extension of the static inventory problems under uncertainty, and we will refer to this kind of problem also. Okay. So now during this lecture session, I will first refer to the general characteristics of the problem, static inventory problems under uncertainty. Then what are the possible decision criteria? Then two specific the criteria we will be referring to, with we will discuss them with specific numerical examples. The first one is the World criterion and the second one is the Savage criterion. Okay, so this will be your coverage. Now as far as the general characteristics of this problem is concerned, you may note down several important points. Now as it is a static inventory problem, you are aware that only one order is possible, and this order is to be raised for meeting the demand of an item for a specific time period. Okay, that means the demand is occurring, and for a specific time period, is a limited time period, and what we are assuming that one order is sufficient to meet the demand. So this is the first characteristic. The second one is the demand levels of the inventory item under consideration are not known, in the sense that the probabilities of possible demand levels are not known. So, what we have mentioned when we refer to static inventory problem under risk, we are saying that against the demand of an item, the corresponding probability distribution of demand is known, and then only we are saying that this is the problem under risk. Now, here in this case, when we are saying that the problem exists under uncertainty, we are assuming, and that is the assumption, that the probability distribution of demand is not known. There could be some some information related to demand, but with that information you cannot conclude anything about the distribution of demand. So that's why you are saying that the demand levels of the inventory items under consideration are not known and corresponding the probabilities. If the inventory is a new one and past data related to its demands are not available, obviously if it is a new situation, so you don't have any the past data related to the demand of the item, that means forget about the objective probabilities of demand, even you may not have the subjective probabilities against the demand. So this problem is of uncertain demand, right? Next one is what we might say, that we might conclude in many cases that if the demand distribution is not known, you might conclude that there is no information, but that is not the case. That's why we have mentioned that it is not the case of no information about the demand level. If no information is available, means nothing is known about the level of demand or the characteristics of demand, obviously no analysis is possible. So we are not considering such an extreme case. So what we are saying, that we have some partial information related to the demand of the item, and to what extent you can use this partial information logically, scientifically, so that the order quantity you can determine. Our basic purpose is, under this situation, are you in a position to determine the order quantity for the given inventory item? So that is our decision variable. It is assumed that the partial information about the demand in terms of, say, mean, standard deviation, etc., is made available. Later on you will come to know that how do you represent this partial information. Okay. So usually this partial information is expressed in terms of the moments of the distribution. So we will explain it in detail in the later section of this particular presentation. However, with the available information, no conclusions can be drawn about the distribution of demand. This point we have already emphasized. Hence, the kind of analysis to be adopted for determination of the order quantity, that is the decision variable, is referred to as distribution free analysis. So in the textbooks, in many cases you come across such a situation. That means can you go for say the distribution free analysis to determine the order quantity, that is the decision variable. Okay. So please remember this particular point. That means here, whenever we are saying that the problem exists under uncertainty in respect of the demand of the inventory item, essentially we will be using distribution free analysis. This is a problem quite frequently occurring in the domain of inventory management. This point already we have emphasized. We need to study a number of approaches, simple in nature, for solving this problem. That means under distribution free analysis, a number of approaches you should be aware of, and one by one, in a systematic manner, we will be discussing all these important approaches. So you have to take a decision related to, say, the order quantity. Now, obviously, it is suggested that why don't you use certain decision criteria. And if you go through the literature, what you will find that the researchers, the practitioners, they have been suggesting a number of decision criteria. And first you should be aware of what are the possible decision criteria. And you also must know that in a given situation, which particular decision criterion is appropriate. So, we will first discuss what are the possible decision criteria that you may adopt or that you may use for solving a static inventory problem under uncertainty. Now, few comments we have made. We are aware that in problems under risk, the demand probability distribution is known or specified either in empirical form or in standard form. However, here in this case, this distribution is not known, whatever may be the reason, right. So, this is the point to be underlined, that is, whatever may be the reason. We need to solve the problem even if the probability distribution of demand is not known. That means you cannot say that that as the demand distribution is not known, how can there be any say the inventory control systems for the given item. So, you can't say so, and that is why you have to think of other or appropriate ways and means to solve the problem. To solve the problem means that you need to determine the order quantity. Okay. So, the researchers in the past have suggested a solution of this problem based on the selection of the decision criterion. Okay. So, already it is there. Now, if you go through the literature, you will find mostly one of the three important decision criteria you may use. So, very soon you will come to know what are these three decision criteria. So, that is why we are saying that there are three decision criteria recommended. You may select any one of these criteria for solving the problem. So, what are these three decision criteria? The first one is the so-called the minimax or maximin criterion proposed by Abraham Wald, and that is why it is referred to as the Wald criterion. So, we will explain that how do you use this Wald criterion for solving the problem. The second one you may opt for, that is referred to as the Regrade criterion proposed by Leonard Savage. That is why many a time it is referred to as the Savage criterion. And the third one is the Equal probability criterion. It is proposed by Bayes, but extensively used by Laplace, okay, two great mathematicians. So, that is why it is referred to as the Bayes criterion. Now, let us first talk about Wald criterion. How do you use Wald criterion? It's very simple. If you refer to our previous discussions or the last week say or the previous weeks so the discussions on inventory problem, what you are aware of? You are aware of the payoff matrix. Okay, so when so the demand levels are known with their probabilities. So, obviously, you need to identify or you need to know that what are the possible order strategies. So, possible order strategies versus the possible demand levels with their probabilities, these are known, and for each combination of order strategies and the demand level, you need to calculate the outcome or the payoff either in terms of profit or the contribution to profit or in terms of say the cost. So, this exercise already we have carried out in the previous lecture sessions. So, the first what you need to do here also when you try to apply the Wald criterion to solve the problem under uncertainty, the first you have to create a payoff matrix or outcome matrix. Okay, so this procedure is known to you. For the given problem, follow the procedure described in week 3 lectures. I have already mentioned. So please refer to the week 3 lectures. You will get the details. For each possible order strategy, that means order quantity, possible order quantity, select the worst outcome or the payoff. Okay, so that means against a particular order strategies, there could be the different the possible demand levels. Now, against which particular demand level you get the worst outcome or the payoff. Is it okay? So if it is in terms of profit, obviously you search for that particular demand level for which you get the minimum payoff, whereas that means the minimum profit. Whereas if it is in terms of the cost, that means the payoff matrix you have created in terms of the cost, that means you select that particular demand level against a particular order strategy for which the outcome is, or in terms of the cost is worst, that means the maximum cost value. If the payoffs are in terms of profit, the worst is the minimum value. If the payoffs are in terms of the cost, the worst is the maximum value. Is it okay? So it is well understood. We select that order strategy which has maximum of such minimums if payoffs are in terms of profit. This strategy is referred to as maximin strategy. So I repeat, we select the maximum of such minimums. That means against all the demand levels you get say with all order strategies you get the minimum values, and now you try to maximize these minimum values. That means the maximum of such minimums if payoffs are in terms of profit. That's why it is referred to as maximin strategy. First you go for the minimum one and then you try to maximize it. So the maximum of the minimums, that's why it is referred to as maximin strategies. Whereas if the payoffs are in terms of the cost, what do? You select the minimum of such maximums. That means this strategy is referred to as minimax strategy. That means first you select the maximum value, that means the maximum cost, that is the worst value, and then out of all possible maximum values you search for the minimum one. That's why it is referred to as the minimax strategy. So you just remember the two strategies. The first one is the maximin. Either it could be maximin strategy or it could be say the minimax strategies. Now here is an example. Suppose the payoff matrix in terms of profit. So it is the 3 by 3 matrix. So the demand is occurring in 3 levels, either 1, 2 or 3. So the order quantity could be either 1, 2 or 3. So there is just an example that the cost the values are given obviously, and as well as the sale values are given in a given numerical problem. So with the given data related to the cost as well as the sales, so you can calculate the payoff. Is it okay? That means if the order quantity is 1 and the demand is also 1, what is the corresponding payoff? So the payoff is say 3.5 in monetary terms, and similarly for all other the combinations, like say if the order quantity is 3 and the demand level is 1, that means the corresponding payoff is 0.50. Similarly, if the order quantity is 3 and the demand level is also 3, the corresponding say the payoff, is it okay, at this combination the payoff is 10.50. Okay, so this way you create this payoff matrix in terms of profit. Next, what do you do? The worst values for each order strategy. So you select the worst value. That means if you refer to this particular say with the table, what do you find? That against order 1 the worst value is 3.5, because in this case is a very particular case, all the values remaining same, so it is 3.5. For order quantity 3 the worst value is 2. Obviously this is the worst values, and for order quantity 2 the worst value is 2, and for the order quantity 3 the worst value is 0.50. Okay, so next what you find, that means you have identified against each order strategy the worst value. So order 1 3.5, order 2 2.0, and order 3 the minimum payoff is 0.50. Hence maximum value of the minimum or the worst value is 3.5, and hence the order quantity is 1. So this is a very the simple approach, and I hope that you have understood what is the basic the idea. Now just keep in mind that when you opt for Wald criterion, actually it is referred to as a conservative you become conservative. That means in the sense that you first try to protect yourself against worst possible situation. Is it okay? So this approach is a conservative one, but in many cases when you try to avoid risk, means first you must get an assurance that what is the minimum say the payoff I should be assured of. So if you try to say create a situation where the minimum payoff is assured, obviously you will opt for Wald criterion. Now the alternatively you can also use the Savage criterion. Now in the Savage criterion, so how do you use the Savage criterion? With respect to the payoff matrix created for the given problem, calculate the regrets or the opportunity costs under all possible demand levels for a particular order strategy or the quantity. Now in the previous lecture sessions we have referred to the opportunity cost matrix. So how do you create these opportunity cost matrix? The methods or the method to be used is also very clearly explained. So the first you create the payoff matrix, and this convert the payoff matrix into the opportunity cost matrix. Okay, so and obviously you will find that when you get the opportunity cost matrix, you will find that all the diagonal elements there they do not have any value. That means all the diagonal elements are zeros. So that means when the demand is exactly matching with the order quantity, that is the best possible decision, and obviously you don't have any regret. That means there is no the cost associated with loss of opportunity. You are not losing any opportunity, so that's why there is no loss associated with the lost opportunity. So that is the best possible strategies. Whereas for all other combinations where the demand is not matching with the order quantity, either the demand is greater than the order quantity or the less than the order quantity, what you will find that you are incurring certain cost, and this cost is referred to as the opportunity cost. So when the demand is more than the order quantity, obviously it is a stock out situation, whereas if the demand is less than the order quantity, it is an overstock situation. So we have already computed that what is the cost associated with overstocking per unit basis, or what is the cost associated with say understocking unit basis. So when you refer to the say the opportunity cost matrix, you have you will get two such important information. So with respect to the payoff matrix created for the given problem, calculate the regrets of the opportunity cost. Is it okay? That is the first thing you have to do, the first exercise you carry out under all possible demand levels for a particular order strategies or the quantity. Once this is done, that means when the regrets are computed for each possible order strategy, a regret matrix in terms of the opportunity cost is formed for the given problem. This point already we have elaborated. Apply minimax criterion to regret matrix to get solution, that is the order quantity. That means here obviously it will be minimax, because if you remember that if you refer to the payoff matrix, now the payoff matrix could be in the form of the cost. So if the payoff matrix is you create in terms of the cost, obviously you have to apply the minimax strategy. So the minimax strategy you apply over here, because this is a table or this is a matrix you have created the in terms of the opportunity cost. So here is an example. Suppose the payoff matrix in terms of profit is as follows. That means again the same table you refer to, same table, like you have 3 demand levels. This is just for illustration purpose, so that you have a proper understanding of a particular criterion and how do you use this particular criterion for solving the problem. So suppose this is again a 3 by 3 matrix. That means the demand occurs at 3 levels and one of the 3 levels, and similarly so that there could be 3 possible order quantities, 1, 2, 3. Demand is 1, 2, 3. So we have computed the payoffs. So in terms of the profit, that is 3.5, 3.5, 3.5 and all other combinations, right? So so this is your the profit matrix. Now what do? You apply the regret matrix. So how do you compute the regret matrix? It is essentially the opportunity cost matrix. So just you refer to this particular table. What do you find? That when the demand is 1, if you order for 1, you get a value of 3.5. If you order for 2, you get a value of 2.00, and if you order for 3 units, you get a value of 0.50. So obviously the payoff matrix is in terms of profit. That means the higher values are always preferred. So the 3.5 is the maximum one. So obviously if you go by this the column values, you will find that against so the demand level 1 and against the order quantity 1, so you don't have any regret. That means 3.5 is the maximum, and maximum value is 3.5. So how much is your regret? How much is the opportunity cost? That is, you subtract the maximum from the value which actually you have obtained. So the maximum is 3.5, and how much you have obtained, that is 3.50. So obviously you don't, the value is 0. That means there is no regret, there is no opportunity cost. When you get a return of 2, that means outcome is 2, obviously this 2 should be subtracted from the maximum value, that is 3.5. So what is your regret? What is your opportunity cost? That is 3.5 minus 2, that means 1.5. And when you ordered for 3, you are getting a return of 0.50. So how much you are losing from the maximum? That is 3.5 minus 0.50, that means 3. So same logic you apply for the second column. What you find when the demand is 2, and so if you go by the column values, you will find that against order quantity of 2, you get the maximum value, that is 7. So when you get 3.5 against the order quantity of 1, how much you are losing? That is, you subtract 3.5 from the maximum, that is 7 minus 3.50. That means here it is 3.50 will be your opportunity cost. When the order quantity is 2, obviously the opportunity cost will be 0, 7 minus 7, and when the order quantity is 3, you are getting 5.50. So how much you are losing? That is 7.00 minus 5.50, that means 1.50. So same logic you apply to calculate the opportunity cost for the elements in the third column. Okay, so we have this regret matrix. So obviously we will find that all these diagonal elements are zeros, and all other elements, like say when the demand is 1, your order quantity is 2. So how much the regret you have, that is 1.50. When the demand is 1, the order quantity is 3. So obviously your opportunity cost is 3.00. Okay, so similarly, when the demand is 2, order is 1, it's not a perfect match. Obviously, you are losing something, so that is the opportunity cost. This is 3.50. When it is 2 versus 2, there is no opportunity cost, and when it is against 2, when the order quantity is 3, again you are losing 1.50. That means here what you find, if you look at this table, you get a regret matrix. So regret matrix, opportunity cost matrix. Now what do you do? This payoff, this is another kind of payoff matrix essentially, but in terms of the opportunity cost. So you have to apply the mini-max criterion. So what is the result? That means maximum regret against order quantity 1 will be 7, against order quantity 2 3.50, and against order quantity 3 it is 3.00. Hence the solution is minimum among the maximums. So that is the mini-max. That means first you go for the maximum value and then you try to minimize. So minimum among the maximum, that is the 3 units. That means the order quantity is 3. The minimum value is 3.00, and against 3.00 the order quantity is 3. That's why your decision variable order quantity is 3. Now from the regret or the opportunity cost matrix, we have 2 important information. The first one is unit overstock cost, and the second one is the unit understock cost. So if you refer to the regret or the opportunity cost matrix already developed, okay, what we get, unit overstock cost is equals to 1.5 in monetary units, and unit understock cost is 3.5. Now here one important point to be noted. You know, whenever we try to assess the quality of any inventory control system against a particular item, now we have many kinds of say the performance measures when reflecting the quality of inventory control system. Now one is that at any point in time against a particular say or say during a period of time, how much overstock you carry, and simultaneously are you facing a situation where for the same item you face an understock situation. Now in most cases when you go for empirical analysis or empirical study, what you find that you need to calculate say overstock cost per unit basis, that is preferred, or you need to calculate or need to estimate the understock cost. Now in almost all cases what you will find that understock cost is always significantly more than overstock cost situation. So if you have a choice between say minimization of understock situation or understock cost or minimization of overstock cost, obviously your first preference should be that minimization of understock cost. So with this the reference I conclude this session, and in the next sessions I will be starting with another decision criterion called equal probability decision criteria. Okay, so thank you.